When the VGA interface was introduced, CRT monitors or cathode ray tube monitors were the common monitors used for computer screens and even for TVs. Nowadays, these monitors are quite outdated and you probably won't see them. If you see them, it's probably in an older system. However, understanding how they actually work will help us understand how VGA works and will help us ultimately design a video controller that can actually utilize the VGA protocol. So in this video, I'll just go through briefly about the basic operations of a CRT monitor. So in here, what I'm showing you is a CRT monitor, or actually the tube itself. So it consists of what we call an electron gun, and the electron gun is just basically simply a coil, usually a tungsten coil or some other material. You apply certain voltage across it, there's a current, and what the current does is actually heat that coil, and when you heat that coil, you excite the electron, and at the outer orbit, these electrons just jump. What you do is you capture them with some sort of electric lenses, and these electric lenses capture all these electrons and form a beam. And generally speaking, that beam gets directed to some sort of a fluorescent screen on the other side. Okay, because the electrons are negatively charged, so generally you'll see that there's a positive charge in here and negative charge in here, so that the beam actually traverses or travels to the fluorescent screen. And that's why we call this here as a cathode. Okay, and that's actually stands for the C in CRT. So that's why we call them cathode ray tubes. So we call them ray, the R in here, because you're forming an electron beam or ray, and it traverses a vacuum tube. So that's actually what the T stands for, because there's a tube in here. Okay, so that's what CRT stands for. So effectively what you're doing is you're generating an electron beam, and you're letting that beam actually hit some sort of a fluorescent screen, and that fluorescent screen will emit light for a very brief period of time. And afterwards it just basically does not. So what you do is you continuously change the beam or change something, or actually scan that screen so that you display certain useful information on it. So that's the basic of how a CRT works. However, if you think about it, we're not talking about pixels or doing anything. So if we're taking a look at how the monitor or the screen looks from the front, so this is a cross section of a CRT. This is actually how it looks from the front. We know that it's actually just a rectangle, and we display different pixels because they're arranged in 2D. So how do we display different pixels? Well, as it turns out, that each pixel will have different intensity or different brightness, and the way we control the brightness is actually by this particular signal. We're going to call it mono. So here in this example, I'm showing you a monochrome monitor. It's easily you can easily interpret or interpolate the same idea for colored screens. But now, all you need to know is basically the voltage you apply to here can range between 0 to 0.7 volts, and will actually changing that or will change the intensity of the pixel or whatever it actually hits. So now we know how a pixel value can be changed, and it's just basically by changing the mono. So how can I have different pixels? And as it turns out, that you need to move that particular ray. So the ray actually hits the screen, but you need to actually traverse the screen or scan it in some sort of a pattern. Generally speaking, it's a very systematic pattern, and that pattern actually goes from right to left, okay, and then goes back in here, from right to left, and then goes back in here, from right to left, and goes back in here, from right to left, or actually from left to right. So I've been saying right to left, but it's actually from left to right, and then left to right, and then left to right, and then left to right, all the way down, top to bottom. And then when you reach the very end, you actually go in here with a ray trace, with a vertical ray trace. So how do we change the direction of that particular ray? Well, as it turns out, we actually employ deflection coils. So we have a couple of coils, one horizontal that is responsible for moving the beam left and right, and one vertical, which is responsible for moving the beam up and down. So when you utilize both of them at the same time, you will have this particular tracing pattern. So how do we actually control the deflection coils? Well, the deflection coils are just basically they're coils that surround the ray tube or the tube from the outside and just generate electromagnetic fields that actually changes the beam. And the way we control them is by providing them with a sawtooth signal. And the sawtooth signal, usually for the horizontal, you'll have several of them for one, because you're actually doing back and forth, back and forth, back and forth, back and forth for a single traverse, like downwards. So generally speaking, the horizontal is a little bit faster than the vertical. But anyway, as hardware designers or digital hardware designer, you really do not need to worry about this. What we need to do is actually, we need to provide some sort of a digital signals, and the way you actually generate the sawtooth in here is by providing what we call an H sync or horizontal sync and a V sync, which is a vertical sync, and both of them are actually digital signals. So you provide it to the VGA monitor, and the VGA monitor has some sort of a horizontal oscillator and amplifiers for the vertical and the horizontal, and generate the sawtooth correctly. So our ultimate goal in designing a VGA interface or a VGA controller is actually to do the following. We're going to be generating the pixel value, the intensity value. We're going to be generating the H sync and the V sync. And there's very specific timing in there, because you're going to provide a certain value at a certain time within H sync and V sync, and that will activate a certain pixel on the screen in here. So our ultimate goal in designing that particular driver is actually to figure out how we generate the H sync, how we generate the V sync, and what can we do in terms of pixel values. And they're all digital signals here.